Right. Okay. So we have seen how to import the mesh into the MATLAB, into the Active. Okay. It doesn't matter which one you are using, Active or MATLAB. And we have also seen that we have also implemented the subroutine for calculating the elements difference matrix. Now we are going to combine them to solve this problem. Okay. So so what I have done is, so I have added a function like for plotting. Okay, so we stopped here in the last part. Okay, so now I have added this function for plotting. Okay, so what I'm going to do, okay, so let's create a vector for storing the solution. Okay, so we need the number of nodes as well. Okay, so let us also create a variable number of nodes. Okay, so this we can get from the position field in the MSH object. Okay, so our solution is 0. Okay, so there is not much to see here. Okay, but this try-surf. Okay, so if you're not familiar, so you can check MATLAB or Octave manual, like about how to access, how to use try-surf to plot. Okay, we need to pass the connectivity of the elements. We need to pass the coordinates and y coordinates and the value of the solution, like value of the field at each node. Okay, so we can also use random function. Okay, so just to see what, okay, so if you have our solution, then we will plot the solution. Okay, so let's initialize it to 0 one more time. Okay, so once we have the solution, we'll plot this. So let's now what we are going to do now is, so we have imported the mesh. We know the number of nodes, we know the number of elements. Okay, so we can loop over the gross point, sorry, we can loop over the elements and calculate the elements difference matrix and assemble. Okay, now what do we need? We need to create the global stiffness matrix. Okay, so total DOF, it should be of size total DOF. What is our total DOF variable? Number of nodes multiplied by number of DOFs, and at each node we have one DOF. Okay, this is our scalar problem. Okay, at each node we have one DOF, and then our global force vector. So it is of size total DOF comma 1. Then we have our solution vector, so which we will solve. And remember, for this problem, the solution is 0 on all the boundaries. U equal to 0 on all the boundaries. Okay, but we need to know what are the nodes on the boundary are, right? No. Okay, so we know from MSH object we have lines. Okay, these are our, okay, these are our lines on the boundary. Okay, these lines, that is 1D elements on the boundary. So from these we can get all the nodes, right? So these are the node numbers and this is the tag. Okay, from the first two columns we can extract all the nodes on the boundary. Okay, so boundary nodes are, okay, all the rows but the first two columns. Okay, now if you want to know how this works, okay, so we extract all of them. So something is wrong. Okay, not position, lines. Okay, so we extract all the boundary nodes. Okay, and then we flatten this array. Okay, we flatten this array, and then what we do, we find the unit values. Because there are some duplicate nodes, so we find the unit values. Okay, so we are going to use all these commands. Okay, and then we flatten it, and then we find the unit nodes. Okay, so at this point we have all the unit nodes on the boundary. Now from this we can calculate fixed DYF. Okay, our fixed DYFs are all those nodes values, like node numbers on the boundary, since we have only one degree of freedom. Okay, and then once we know this, we can prepare our free DYFs array, DYFs free. Okay, by doing the set diff. Okay, so first we need all the DYF, and then from this we subtract, or we subtract the set of fixed DYF. From this we get the set of free DYFs. Okay, again we can check here. Okay, so these are the fixed ones. And then if we do this, we get the free DYFs. Okay, these are the DYFs that are inside the domain. Okay, these are the DYFs that are inside the domain. Right? Okay. Now, next we go to the loop over elements. We prepare our local elements stiffness matrix and local force vector. Okay. So this is our function study. Okay. So this is where we calculate our stiffness matrix. We need to make some modifications, but we will see. Okay. So we are going to modify this into a function. Okay, function. We want K local and F local. Okay, from this. Okay, so to calculate the element stiffness matrix and force vector, what do we need? We need the coordinates. Okay, node coordinates. And we need to know the node numbers. What are the node numbers? That is the element node connectivity. Okay, so we can call node numbers. And we need mu, we need f. Okay, we can pass any other information that we need. Okay, so I'm removing this since we pass mu and f. And once we know node numbers and node coordinates, okay, this node coordinates is a global array of xy coordinates. So from this, and based on the element node numbers, we change this to get x1, y1, x2, y2 values for all the 4 nodes. Okay, so this is the x coordinate of first node, and this is the y coordinate of first node. Okay, similarly, we get x coordinate of second node and y coordinate of second node, and so on. By third node, x and y coordinates. Okay, that's all we need to change. Okay, so we earlier we had the subroutine for calculating element stiffness matrix for a particular element with given x and y values. Now we have customized it, not customized, we have generalized it for an arbitrary element where we can pass the node numbers and node coordinates. Okay, and from this we extract the corresponding x and y coordinates for all the 4 nodes. That's all we need to change, and everything else remains the same. Okay, so we can comment them, because we don't want to plot like all these variables. Okay, we can plot if you want. Okay, but let's remind them. Okay, now here what do we need? The first one is the node coordinates, and where do we get it? Using the pos variable in the mesh object. The second one is we need the node numbers of this element. Okay, we don't need node numbers of all the elements. Okay, so we have quads for this element. We pass all the, like we can pass the first four columns because that is where we have the node numbers. We can pass everything, it doesn't change. Then we need mu, we need f. Okay, we have prepared here. Okay, can give mu here. How much is mu? Mu is 1, f is 20. Okay, so we calculate the element stiffness matrix, element force vector, and then what do we need to do? We need to assemble. Okay, global. Okay, and to assemble, we need to know the rows and columns. Okay, the rows is, okay, so we can get from here. Okay, since we have only one degree of freedom, our element node connectivity is same as element devoid of connectivity. Okay, so what we can do, we can create another array element node connectivity, okay, which is this, and our element devoid of connectivity is the same. Okay, I am creating some duplicates here, okay, which we may or may not use, but following our conventions, okay, element devoid connectivity. So here also, like you can use element node connectivity. Okay, it's up to you. It doesn't change how we access and pass. Okay, as long as we do it correctly. Okay, for assembling, we need the rows. So that we need from element devoid of connectivity array. So we need it for the current element. And our columns are the same. Okay, rows, comma, columns equal to k global rows, comma, columns plus k local. Okay, and then similarly for f global rows, comma, 1 equal to f global rows, comma, 1 plus f local. Okay, so we have assembled the element stiffness matrix and element force vector into global entity, global quantities. Okay, now we apply boundary conditions. Since all the boundary values are 0, all the nodes on the boundary have 0 values, we don't need to do anything because the contribution to the right hand side would be 0. But we need to, okay, so if you want, like it depends on how you solve it. Okay, so for simplicity, so I'm going to solve it like this. Okay, so we want the solution at free DYFs only, right? So DYF free, and for this we extract the corresponding rows and columns from the global stiffness matrix and corresponding rows from the global force vector and solve it, and then we populate the solution at free DYFs into the corresponding entries into the solution to the our solution vector. Okay, so if everything is correct, this should work and we should get the solution. Let's see, there might be bugs, but that's okay, it's part of learning. Okay. Okay, that was some issue. To reopen it. Okay, it looks all right. Okay, so there were no bugs. If there are bugs, please check carefully and correct them. Okay, this looks okay. So now the maximum value is 0.739. Okay, we have more than 0.5. Okay, so since the mesh is really close, we may not match the exact value. Okay, so what can we do? We can check the maximum value of the solution. Okay, it is 0.5889. Okay, the mesh is close, so we may not match exactly. So what can we do? We go back here, change the mesh size, let's say 0.05. Okay, I'm going to reload the script. Okay, we have a finer mesh. Okay, if you want, we can use even finer mesh. Okay, let's say 0.02. Okay, so let's use this mesh, and we don't need to change anything about the boundary. We export this. Okay, let's name it as mesh 2. Okay, we export it. Copy the file. Okay, now before we run this, now what do you observe here? So in terms of like how easy it was to extend it for arbitrarily oriented elements. Our mesh is not body aligned. Our mesh is not a Cartesian mesh. Our mesh is arbitrarily oriented, right? So still the stiffness matrix, the way we have implemented, it is applicable to any element. Okay, so this is the beauty of the finite element method. So once you implement the element subroutine, you can use it for arbitrarily oriented element. It is unlike in finite volume method, because in finite volume method things get quite complicated as soon as you go from structured grids to unstructured grids. Okay, now let's look at the finer mesh that we have generated. Okay, okay. Since we have more nodes, it may take a while, but not too long. Okay, yeah. So this is what we expected, right? Okay. Now, what is the max value? 0.6983. Okay, so yeah, that seems to be the okay. So still not good enough. Yeah, but you get the idea. Okay, so this is how we use the finite element method to solve the diffusion equation in 2D. Okay, in the next parts, I'm going to show you how to extend this to problems with Naiman boundary conditions. Okay, adding Naiman boundary conditions is always like adding any boundary terms to any numerical schemes is always challenging. So FEM is no different, but it does make the life easy when we have zero Naiman boundary conditions because we don't do anything. But we will see how to implement those and also how to add non-zero Dirichlet boundary conditions to this code that we have developed. Okay.